All right, so today we're just gonna do practice problems. So before we do the problems, let me just give a quick summary of the type of equations we might be using, okay, to solve the problem. So the first one is always the first principle. Okay, of thermodynamics, which we say is equal to what? Q minus work equal to change in energy. Okay, that's one equation we use, and the other one we use is the ideal gas relation. PV equal nRT. I think this is the N and not the N bar. You have it, I'll find it somewhere here. Yeah, it's not the N bar. Okay, and one more thing that I think I mentioned in the class notes, I remember exactly when, but we say that when you have an ideal gas for an ideal substance, so what I call an ideal substance is basically a substance that remains in the same state. Okay, so if it remains on the same state, what does that mean? That implies that the properties of that substance are more or less going to be constant, because remember, the state of a substance is determined by the value of its properties. Okay, so if the value of properties do not change much, probably the substance is going to stay within the same state. Okay, so you could say that an ideal substance, you kind of make the assumption, is not 100% true, but it means like properties are more or less constant. Okay, and if that is the case, this means that the change in internal energy will be proportional to what? Will be equal, generally will be equal to what? U2 minus U1, which this is valid for any substance. This is valid for any substance, but for a closed system, this would be equal to C sub V, which is the specific heat, times T2 minus T1. Okay, I'm just trying to see if we did cover that or not. Okay, doesn't look like we have covered that, but I just do it now. So basically here I need to give more details then. So this is for any substance, and this would be valid just for an ideal substance. So obviously an ideal gas, a gas is an ideal substance because air always remains in the air state. Okay? All right. So in this equation here, CV is what is known as the specific heat at constant volume. Okay, and basically what is the physical meaning of this constant? So basically, you know, for example, I mean, if you put, let's say if you put foil paper in the oven, the foil paper, when you get it out of the oven, is not hot. Okay, that's because if you want, the property of the foil paper is not to keep the heat within itself. okay? However, if you try to grab the potato in which the foil paper was wrapped, what's gonna happen? You're probably gonna burn yourself, no? That potato stays hot forever. So if you want, one will have a low specific value, a slow retention of heat. However, the potato should have a very high value of specific heat, meaning that it will retain a lot of the heat, okay? So that's the meaning of these constants. If you want, it means like how likely it is that substance to retain heat, okay? All right, and specific volume, this is, if you want, I'm not going to do derivation because it's not bringing much to the understanding, but this is basically means constant volume and basically what I want you to remember of this, constant volume means what? This is going to be all the time related to closed systems. So if you think for a second, what is a closed system? Could be just a rigid container in which what's happening inside, the volume is known, no? It's restricted, correct? And now, what happens if you have the other system will be a piston in the assembly. In this one, also the volume is restrained, no? Okay, it's enclosed. So CV basically means constant volume, but really what it means is that you only use this one for this type of system. Okay? The reason is that then we're going to see there's a C sub P that will mean specific heat and constant pressure, and that will be for the other type of system, which are the ones that are called control volume or open systems, okay, in which you have mass that can flow. All right, but we are not there yet. Okay, so this is very important over here. So this relation here is valid for any substance, but if you can do the assumption of an ideal substance, you can simplify the problem by this. All right, so why I'm doing this about ideal substances first is because these values here, you need to get them from the tables, and I'm trying to delay to the second exam that you have to use the tables. In this case here, temperatures can be calculated, okay? And the only value you need to know is CV, okay? So that's the only reason I'm trying to do. So I think that's about it. I think with this information, we should be able to start solving problems. So let's say here, example. So I went to the textbook and I selected a few examples that I think can be good. So this will be on the version that I give you, 311, problem 311. So let's see what 311 is. Let's see if I can zoom out. No, all right. We have to move the page. So maybe let me pause this for a second. All right. So problem 311, let's do the figure, and then we can read the problem statement. But basically it says that as shown in figure 311, a piston cylinder assembly. So this is important to do the figure, because what does that mean? Piston cylinder assembly means that we're dealing with a closed system. And remember, the way I want the problem solved on the exam is the same way I do it in class. We have the problem statement, but I still do a figure on the solution, no? The reason being is because the fact of making the figure gives you time to think about the problem, all right? It's not a waste of time. Feed it with a paddle wheel. So there's a paddle wheel over here, okay? Contains air initially at P1 equals 30 PSI, so you want P1 equals 30 lbf inch square, and T1 equal to 540 degree Fahrenheit, and initial volume of 4 cubic feet. The air undergoes a process to a final state with P equal 20 psi or lbf per square, and V2 equal to 4.5. So basically there is an expansion, no? All right. So obviously if you expand this, if this moves to the right, the pressure is going to go down. I mean, should not go down if this wasn't there. If nothing was happening, it should be constant, the pressure. But during the process, the paddle will transfer energy to the air by working the amount of 1 BTU. So what does that mean? Is that the work, this is given, the paddle wheel is given 1 BTU of work. Is that, I mean, on the figure they have it correct, is that positive or negative? On the textbook convention, when something goes in is negative, no? Yeah? So it should be really -1. I just put it with the arrow, but just look at here if you want to put -1 as they have it over here. And then what do they say? I think this one is wrong because if it's negative, that means that it's coming out, but let's see. And there is energy transferred to the air by the heat. And there is energy transferred to the air by heat in the amount of 12 BTUs. So that one, I think I kind of disagree with the sign they put there. 12 BTUs. So I think that should be positive because that should be then, let's read this one because during the process, the paddle will transfer energy to the air. So this gives energy to the air by working the amount of 1 BTU. And there is energy transferred to the air. So from here to here in the amount of 12 BTU. Okay. To me, this should be positive value. Assuming ideal gas behavior and neglecting kinetic and potential energy effects, determine the temperature of state 2. So we need to determine T2. We can use the ideal gas assumption, which would be the ideal gas or the ideal substance, the temperature at T2, and the energy transferred by work from the air to the piston. But they give you the value. Oh, by work from the air. Okay. I need to find, then if you want work, what I will call this one instead of air, I will call it work piston. All right, so let me move this up. This is what I have on the figure. Okay. All right, so let's see. Over here, as state 1, we know P1, T1, and V1. Okay, so basically we know everything. And do we know what is the substance? They say it's air. So here, this is air. Okay. All right, so here what we can do is probably use the ideal gas relation. So using ideal gas relation, what do we know? We know that P1, V1 will be equal to NR T1. And we also know what? That P2, V2 will be equal to NR T2. So let's see over here. We know P1, T1, P2, T2. Okay, so I think here we could write what? We could do from these two relations, we could just write that P1, V1 divided by P2, V2 will be equal to what? nRT1 divided by nRT2, we just give P1 V1 divided by P2 V2 equal to T1 over T2. Okay, and from here we could just say that T2 will be equal to T1 times P2 V2 divided by P1 V1, or this could just be T1 equal to P2 P1 V2 V1. So if we do the numerical application, we can get T2 will be equal to what? T1 is equal to 540. Here units do not matter because they will cancel out. P2 is 20. P1 is 30. So that's 2/3. V2 is 4.5. And this is 4. So, I mean, I have here the solution, but they did it differently, but hopefully we'll get the same thing. Can somebody check? This gives about 750. Can someone check?
720.
720. Is that what you get? 720?
I don't believe the question was asking for Fahrenheit.
Ah, okay, we can move to Rankins, correct. So what do you get here in Fahrenheit? What do you get if you do this? Then we can go back to the question. What happens that maybe they ask you to, in Rankins?
405
So it gives you
Yeah,
405? Okay, so 405. And now to, or in Rankins, that will be what? You need to add, see, we did this. How do you go from Fahrenheit to Rankins? You need to add, remember I tell you to bring that page with the units? 460, okay? So that will give you then 865. Okay, and B, the energy transfer. All right. Okay, so next, now we need to find the work done by the paddle wheel. Okay, so basically here we're going to say that first principle of thermodynamics is heat minus work is equal to the change in energy, and here is equal to the change in internal energy plus the change in kinetic energy plus the change in potential energy. Okay, in the problem, they tell us to ignore kinetic and potential energy. So we have these two. So basically, the equation here simplifies to Q minus work equal to the change in internal energy. Okay, so over here, now what we can do is, this is equal to Q minus what is creating work in that system. In that system, we have the work done by the paddle wheel. Okay, so let's say paddle wheel plus or minus again, whatever work is done by the piston. So let's say here WP. This is paddle wheel, piston. And this is equal to M. This is equal to, what are the units they ask us to find at the end? The answer, is it per mass? Find in BTUs. Okay, so we need to use the mass then. It's not per unit mass. Okay, so it will be equal to M U2 minus U1. But since we're dealing with an ideal gas, we can rewrite this as M C sub V T2 minus T1. Okay, so now this will give us, if you want, okay, let me do the algebra. Q minus work paddle wheel minus work piston equal to mCV T2 minus T1. So this will give us that the work done by the piston, which is what we're trying to find, will be equal to what? M CV T2 minus T1. Oh, no, sorry. Maybe it's better to put an negative sign here, sorry. So I move this one to the other side, plus Q minus work paddle wheel. Okay, so now the only thing left is to do the calculation. All right, so over here, let's say that given so knowing that CV equals 0.17 BTU LB mass Fahrenheit. That's what they had on that table. Let's do the calculation. We have work of the piston. Let me just rewrite it, equal to minus M CD T2 minus T1 plus Q minus work paddle wheel. Okay, and here, put points over here, sorry, put point over here. All right. So in this equation, we have everything except what? Except for the mass M. However, we can find the mass M how? We can either use P1, V1, or P2 V2, but let's say you use P1 V1 equal to N RT. Okay, where here what do we know? N, the number of moles, is equal to the mass divided by the molar mass, where the molar mass of air is, generally I use 29, but here they have 28.97. Okay, 28.97. All right, so basically what does that mean? So I forgot to put a 1 here. So if we substitute here, we have P1 V1 equal to mass over molar mass RT1, which gives you that the mass would be equal to P1 V1 divided by T1 times the molar mass divided by the gas constant. And here, remove these points here. Sorry for that. This is the first law, not the second law. Remove those little points. Otherwise, we need to talk about mass flow. There's no mass flow. All right, so let's do the calculation in 2 parts. I was just going to substitute this one here, but I think it's going to be more complicated. So let's first do M. So if we do the numerical application for M, so what do we have? Be careful here with the units, because P1 is given to us as being equal to 30 30 lbf in square. But now V1 is equal to what? It's equal to 4 cubic feet divided by T1, which is 540 degrees Fahrenheit, but that would be 1,000 ricans, no? Plus 460. So we divide here by 1,000 ricans, because that's the unit for temperature. And now times, okay, so we're gonna have to do a unit change over here. So here you can choose, let's transform maybe this inch square into foot, okay? Or you could transform this foot into inches, whatever you want. But let's first look at the units of the other ones. Maybe we can make the decision based on that. And the M over R will be equal to what? 28.97 divided by the R. So this R, again, that should be on the units page that I told you to print and to bring to every single class. But in English units, this is equal to 1,545 foot pound force divided by LB ricans. Okay, so I think that's going to give us the answer of what is the best to do here for the unit transformation. So if we have foot over here, it's better to transform these inches into feet, no? Okay, So this one is divided, so it really needs to go on top. So you know that 1 foot is how many inches? 12 inches. So 1 foot square will be 12 square inch square, no? So 144. Okay, and the value for R we say was equal to 1545. So if you do the calculation, this should give you about 0.324 lb. Okay, so now we can just say substituting into work of the piston equal to minus mCv T2 minus T1 plus Q minus W by the wheel. What do we get? We're going to get this is equal to 0.324. CV is 0.17 BTUs lb mass Fahrenheit. So we need to be careful with this one. Remember here, this will be 0.324 lb mass, so this will cancel with this one, no? We only have BTUs per Fahrenheit. And the temperatures, we had T2 to be equal to 405 Fahrenheit minus was 540, no? The T1 540. Okay. Q for me, if it's going inside the air, as they mentioned, but they don't do it. So if it's going in, should be positive. Okay. Plus 12. And now if you apply work inside here, this one should be negative. So it should be plus 12 BTU minus 1. So what do you get if you do this calculation? Can you please do it? So this is equal to 3.56. So if this is positive, what does that imply? Is that the work done by the piston is actually work coming out, no? Which makes sense. I mean, if you move here fan inside, you're going to move the piston out, no? So the piston should give work to the whatever this is attached to. All right? So that makes sense. In addition to that, we also assume that it was receiving heat. So this is the work done by the piston, 3.56. Okay, guys, so quick correction in this equation here, we forgot to put the minus sign. So actually this gives, the important part is that the value is still positive, but instead of being equal to 3.56 will be equal to 18.44 BTUs. Okay? All right, so let's do another problem. The other example is problem 3116. Okay? And again, let's do the figure. So you have the figure over here. So 2 kilograms of oxygen fills the cylinder. what happened here? Oh, the piston cylinder. Okay, yeah, we can see over here. Assembly. So again, just do here piston cylinder assembly, which means that we're dealing with a closed system. Again, in the exam, I want to see the same way that I do in class. You see, I do a figure, even though it's in the problem statement. So it looks like they do here, O2, and then this is going to expand. All right, so 2 kilograms of oxygen. So this is oxygen, O2, M equal 2 kilograms. Fills the cylinder with piston cylinder assembly. The initial volume and pressure are 2. So volume is 2 cubic meters. And initial pressure of 1 bar. All right? Respectively. Heat transfer to the oxygen occurs at a constant pressure until the volume is double. So basically, they said they put heat over here until, so let's say we go here, something happens in this process, we add heat over here until the pressure is double, or until the volume. Heat transfer to the oxygen occurs at constant pressure. Okay, so constant pressure, so let's say P2 equal P1, that's normal, until the volume is double. Okay, that makes sense. So V2 will be equal to 2V1 equal to 4 cubic meters. Okay, so here this is a very important part over here, is that even though they were not telling you, they tell you here that this is a constant pressure. Okay, but even if in this problem they don't tell you that this happening at constant pressure, you should know that the pressure is constant. Because what's happening here, this is a little bit different than before. This is a free piston, no? Yeah, there's no paddle wheel or anything inside. So what is the function of the piston? Is that if you add heat, what's going to happen? If this was closed, what happens is that the pressure inside will increase, all right? But let's say now you add heat, which is what's happening in this case. So there will be more energy here, but what will happen? So the air molecules or the oxygen molecules will want to occupy more space, okay? And if this was a rigid wall, this will increase the inside pressure. But in this case, this is free to move, no? So as the oxygen wants to take more space, this can move freely. And that means that what is going to be constant inside will be what here will be the pressure. Yeah, does that make sense? Okay, this is important to understand, okay? So even though we're not telling you this was a constant pressure, you should know that, all right? Heat transfer to the oxygen occurs, okay, we did that. Determine the heat transfer for the process in kilojoules. So we need to determine, this is now Q dot, this is Q, find in kilojoules. So this is a question mark. We need to find, determine the heat transfer, assuming specific heat ratio is constant, K. So we use K equal 1.35. Kinetic and potential energy can be ignored. So kinetic and potential energy can be ignored. So I put 0 over here. All right. Okay. So in this problem, let me close this. I don't know why they give you the K. I mean, I know why, but it's just going to make things more complicated, which they should not be, but let's just do it as a textbook once. All right, so over here again, we need to find the Q. So what is the relation which is going to give us the Q? It is using the first principle of thermodynamics, which is what? heat minus work. If we ignore the kinetic and potential energy, we are just left with the internal energy. Okay? So over here, what are we going to have? We're going to have the heat that we're trying to find. So basically, it's going to give us that the heat we're trying to find is equal to the work done by what? The work done by the pressure, no? By the constant pressure, plus the change in internal energy. And we know that oxygen is an ideal gas. Okay? So from here, we can just say that plus what are the units we need to find out in kilojoules? So plus M CV T2 minus T1. So basically this is du, no? Okay? All right, so what do we know here? We know it's a process at constant pressure. So for constant pressure, we know that the work is equal to what? PdV. So if it's constant pressure, that means that the work done by the pressure will be equal to P V2 minus V1. I mean, I could change many things here, but yeah, I'm not going to complicate it. So basically, this will mean that Q will be equal to what? P V2 minus V1 plus M CV T2 minus T1. I mean, you could solve the way it is now. You just need to find T2 and T1, which is not given to us, but we could actually go and find them. Okay, but let's do it. Let's see if we can do it another way. Okay. So using ideal gas relation, what do we know? PV equal nRT. So this will mean that T is equal to PV divided by NR. Okay? I don't know if it's going to be easier or not, but so we can find that Q is equal to P V2 minus V1 okay, of plus M CV divided by NR so P is constant, yeah? So it will give you P, could put a P, okay, let me just see over here, P1, P2 V2 minus P1 V1, but you know that P1 equal P2, and N equal mass over molar mass. So this will simplify to what? Equal to P V2 minus V1 plus, a bunch of stuff will cancel here. So this will cancel. N is M over the molar mass. So the mass will cancel. So it will be equal to what? Molar mass divided by R.
Can you move the paper up a little bit?
Yeah, sorry.
Thank you.
So this will give you see what I'm trying here? I substitute the N, so it gives you the mass. This mass will cancel with this one, but this is divided, so it goes up, N divided by R, P, and this will be now V2 minus V1.
So, did you drop the specific heat?
No, you cannot drop. I forgot that specific heat. Sorry. So this will be CV here. All right. I forgot about the CV. Thank you. So this will give you what? We can factor out by P V2 minus V1. Factor of 1 plus M CV over R. Okay, so here we will do the calculation, but I'm just going to give you the value because I will give you the value if it was an exam. So page 32. This is one of those equations that I don't give in class because I don't think they bring anything. They just complicate the problem. I don't know why they just don't give you the value. Let's see, equation 347B. There we go, we're getting close. All right, so 348. 347B, they tell you, see that CV is equal to R. So if you want to write it down, CV equal to R divided of K minus 1. Okay, so I'm just going to tell you here that for O2, this will give a value of CV equal to 0.742 kilojoules per kilogram Kelvin. But we don't want the kilograms here. Let's do the calculation because I think here they did it per unit mass. Okay, let's do the calculation because I copied this one, but I don't trust it. So let's say this would be R equal to, so for K in this problem, they tell us to use 1.35 minus 1, and R is equal to the 8.314. So what do you get for this one? $23.75. Okay, but now still going to be high. Okay, I need to look here at the units for a second. Hold on. All right, so this one, so at the end, what we're going to have on this calculation. So substituting into this equation here, Q equal to P V2 minus V1 times 1 plus M CV over R gives you what? So we need here to be careful because P1 is 1 bar. 1 bar is equal to what? 100 kilopascals. So this would be equal to 100 kilopascals. This is our 1 bar. Okay. Now here the units, we have that in cubic meter, so that's fine. V2 we have 4 minus 2.
You can do an atmosphere, doesn't it? The pressure.
Let's check that. I thought it was bars, but I think we'll go 3116 on oops. 1 atmosphere. Okay. So let's change that one then. You're correct. I don't know why I had bars.
1 bar in the paragraph, and it says 1 atmosphere.
Yeah, I mean on the previous figure the same thing. At least is I think this book is figures, but here it says 1 bar on the front. So let's use 1 bar, okay? Basically, it should not be a big deal because one atmosphere is about 1.04 bar. So it should not be a big deal, but good call. I mean, you see the book is not very consistent with the text and the figure, so we need to be careful with that. So let's use 1 bar. All right, so 4 minus 2, and then we have times 1 plus the molar mass of oxygen, so M of the oxygen O2 should be what is about 32, no? Because O is 16, O2 will be 32, okay? Plus 16. Now plus the CV we'll calculate it, which is about 23.75. But again, if we divide this one now by the R, which is 8.314, we get about the 4 over there. So if we do this calculation, what do you get for Q? So again, guys, like I was saying, like maybe our speaker is that that value looks a little bit high to me. The only problem I see here is when we did this calculation here for the CV, we forgot track of the mass, no? It disappeared. So, and this problem mentioned that it's 2 kilograms of mass. So I think the amount of mass should affect actually how much energy you have, no? So let's see what's happening over there. Hold on 1 second. All right, guys, so I will recheck here these calculations because that value looks high. And if there is any modification, I will put it within the updated PDF file. all right, in addition to the video.
It looks like there are like 4 people who had questions